You're welcome.
Okay, so this is lecture 4 on Gaussian elimination, in section 1.4. Let me write lecture 4. And this is a method to solve a system of linear equations, and it's based on the notion of equivalence. So here we have one system of linear equations, m equations and n variables. And here we have a different system, the same number n of variables, but you can't have a different number of equations. And we say these two systems are equivalent if they have exactly the same solutions. So if the problem is to solve this first system and you're able to solve the second, then you've solved the first, because every solution of this is a solution of this, and conversely. So then the question is, if you're given a system of equations, can you find an equivalent system that's maybe easy to solve? And there are three elementary operations on a system of equations that give you an equivalent system. So the first one is obvious. You can interchange two equations. So here I have a system, first equation, second equation. This is a different system. Why are they different? Because the first equation is not the same. The second's not the same, but all I did was switch them. So any set of numbers x, y, and z that satisfies these two equations obviously satisfies these two equations, because they're the same equations, just in an opposite order. So you can always interchange two equations and get an equivalent system. Second thing you can do is multiply any one of the equations by a non-zero scalar. So here I have this system of equations. Suppose I just multiply the first equation by 7. If I multiply this by 7, I get 7x minus 56y plus 21z equals 7. And I don't do anything to the second equation. And this system has the same solutions as this, because if x, y, z satisfies this equation, it satisfies this equation, and conversely. So I can certainly multiply an equation by a non-zero scalar, and that gives me an equivalent system. And the other thing, yes, go ahead.
Can you please re-explain that again? That was a little confusing.
You take one equation and multiply it by a number. Like here in this example, how do I get from this equation to this equation? I multiply by 7.
Oh, so you only take the first number, right?
Well, I don't know what you mean by the first number.
The constant. You just said multiply by 7.
You multiply it. It's just like if you have the equation 2x equals 3. If you multiply it by 7, you get 14x equals 21. You multiply, when you have an equation, you can do anything to one side if you do the same thing to the other side. So if I multiply this by 7 and I multiply this by 7, this is what I get, and this is a valid equation.
Okay.
If 2x
and another.
Yeah, go ahead.
Oh, another question. So are you multiplying it by 7 because it's missing a constant in front, like the x?
No, doesn't matter.
No?
I mean,
oh, it doesn't matter. Okay.
I'll make this 9. And then this, if I multiply by 7, this becomes 63.
Okay.
You can multiply any equation by any non-zero number, and you get an equivalent equation.
Okay.
It's
that makes
just
sense.
like,
Thank you.
You know, if 3 equals 3 and you multiply by 7, you get 21 equals 21. I mean, they're the same. One's true if and only if the other is true. So you can always multiply an equation by a non, you can't multiply by 0. That makes, it just says 0 equals 0. And you don't get an equivalent system, but you can always multiply by a non-zero scalar. That means a non-zero number. And the third thing you can do is you can add a multiple of one equation to a different equation, another equation, and get an equivalent system. So suppose you have the system 2x plus 3y equals 1, 5x minus 2y equals 9. So if I multiply the second equation by 2 and add it to the first equation, what do I get? So in this, I'm going to add 2 times the second equation to the first equation. What is 2 times the second equation? If I multiply this by 2, I get 10x minus 4y equals 18. And the first equation is 2x plus 3y equals 1. So if I add 2 times the second to the first, I get 12x minus y equals 19. So I got this equation by adding 2 times the second to the first. So from this system, I get a new system where the first equation now is 12x minus y equals 19. And the second doesn't change. So how did I get from this system of 2 equations and 2 variables to this equation, this system of 2 equations and 2 variables? The second equation doesn't change, but the first equation changed. And how it changed is I added twice the second equation to the first, and that's how I got that. And this system has exactly the same solutions as this. So these are the 3 operations you're allowed to do to a system of equations, and you get an equivalent system. And let me just give some examples. This is just some examples from the text, so it's maybe easier to follow when you're just studying by yourself. So suppose we have this system of 3 equations and 2 variables. 4x plus 11y equals 115. X plus 7y equals 67. 8x minus 5y equals minus 13. So this is 3 equations in 2 variables. Suppose I do the following operation. I interchange equations 1 and 2. This is equation 1, this is equation 2, this is equation 3. So when I interchange equations 1 and 2, the second equation becomes the first equation becomes the second, and the third equation doesn't change. Right? I'm just switching equation 1 and equation 2. Right? Suppose I get a new system if I decide, let's say I want to multiply equation 1 by the number 3. So here's equation 1. If I multiply it by 3, I get 3x plus 21y equals 3 times 67, which is probably 201. And the other equations don't change. Now, Let me do, what is the third operation? I can multiply
Add, I think.
an equation by a number and add it to a different equation. So I'm going to add minus 2 times equation 1 to equation, sorry, I'm going to minus 2 times the second equation and add it to the third equation. So I'm not changing the first equation. I'm not changing the second equation, but I'm adding minus 2 times the second to the third. So if I take this second equation and I multiply it by minus 2, minus 2 times 4 is minus 8, minus 2 times 11 is minus 22, minus 2 times 115 is minus 230. I'm going to add that to equation 3. This is equation 3, 8x minus 5y equals minus 13. When I add them, these cancel. I get minus 27y is minus 240.
I have a question because I'm still a little confused. Where did you get -2 from? You just chose it. You just chose it because it's not a zero,
I'm just
right?
showing you how these operations work. There's no strategy here. I could pick 1,000,007, right? Doesn't matter what number I pick. All I'm saying is that these operations, I start with a system of linear equations. I just got 4 other systems, and these other systems have the property that they're equivalent to each other. They have exactly the same solutions. Right? That's all. Now, it just happens that in this final one, I have this equation, minus 27y equals minus 243, which means y is minus 243 over minus 27. And if you divide, you see that you actually get 9. So for this system of equations, y has to equal 9. But we also have x plus 7 times y equals 67. So if y is 9, that says x plus 7 times 9, which is 63, equals 67, which means x has to equal 4. So by doing these crazy operations, we were just lucky, and we found that this system of 3 equations and 2 variables has exactly one solution, xy equal to 4, 9. And you can check if you plug in 4 and 9 into all these equations, they work. But that was just a coincidence, perhaps. This is just an example to show you what these operations are. So there are 3 elementary operations on a system of equations that produce new systems that are equivalent to the original. So you're changing the equations, but the solution space does not change. Okay. And the question is there a smart way to choose these elementary operations?
Yeah, when the hell did I receive?
Sorry, is there a question?
No, sorry.
So is there a smart way, a smart strategy to do these elementary operations to give you a solution of your system of equations? Or to show there's no solution? Because sometimes a system of equations doesn't have a solution, right? That's the way it is. So let me just give an example of one strategy to use to solve a system of equations. Let's see. So suppose I have the following system. 9x plus 11y equals -1, and 5x plus 3y equals 3. So let's say you pick the first variable, which actually shows up in an equation, that's x, and do something so the coefficient of x is 1. So, for example, if I take this system and I don't do anything to the second equation, I don't do anything to the second equation, but I multiply the first equation. What do I multiply the first equation by so the coefficient of x is 1? I can multiply it by 1/9. So if I multiply this first equation by 1/9, it becomes x plus 11 over 9y equals -1 over 9. So all I did was I made this coefficient 1 by multiplying this equation by 1/9, or the same thing, dividing the equation by 9. And now I can eliminate the x from the second equation by doing what? Well, if I multiply the first equation by -5 and add to the second equation, it kills the x, right? Here, let me just do this. If I multiply the first equation by -5, what do I get? I get -5x minus 55 over 9y equals -5 times -1/9 is 5/9, right? That's what I get if I multiply the first equation by -5. And then I take that and I add it to the second equation. And what do I get? These cancel. 6 minus 55 over 9. Well, you have to know fractions. That's -1/9 y. And 5/9 plus 3, that's 27 plus 5, that's 32 over 9. So if I don't do anything to the first equation, but I add -5 times the first equation to the second equation becomes -1/9 y equals 32 over 9. If I multiply the second equation by -9, I get y equals -32. If I subtract, now I don't do anything to the second equation, but if I take the second equation times -11 over 9, I get -11 over 9y is -32 times -11 over 9. If I multiply that, I get 32, I think 352 over 9. And if I add that to the first equation, x plus 11 over 9y equals -1/9. When I add, these cancel. I get x equals 352 over 9 minus 1 over 9, which is 351 over 9, which happens to be the number 39. And lo and behold, we have a miracle. I started with this system of 2 equations and 2 unknowns, and this is an equivalent system, but this is the solution. X equals 39, y equals -32. And I did it by strategically deciding which of these elementary operations to perform. I get one variable to have a coefficient of 1, and then by subtracting suitable multiples of that equation, I can eliminate the variable from all the others. And I just keep doing that. All right.
Is this the Gaussian elimination?
This is Gaussian elimination.
Okay.
So in the notes in the book, there's a long description of how you establish your strategy, how you decide what to do. But it takes it's sort of complicated to explain, and it's easier just to watch me do it, and I explain why I'm doing everything that I'm doing. Let's do another example. I'm picking examples that are worked out in the book, so they're easy to follow when you're studying by yourself. This is 2 equations and 3 variables. 2x plus 3y plus z equals 1. 5x plus y minus 4z equals minus 1. So the first thing I want to do is have one of these variables with a coefficient of 1, and I could use z, but a general rule is maybe if the variables are in like an order x1, x2, x3, or xyz, pick the first variable that occurs with a non-zero coefficient. So in that case, it's the variable x. So if I want to have an equation where the coefficient of x is 1, I can just take this first equation and divide it by 2. If I divide by 2, which is multiplying by a half, I get x plus 3 halves y plus 1 half z equals a half. And I don't change the second equation. 5x plus y minus 4z equals minus 1. And then if I subtract 5 times the first equation from the second, I eliminate the 5x, right? I mean, again, let's just do this as a side calculation. If I take this first equation and I multiply it by minus 5, I get minus 5x minus 15 halves y minus 5 halves z is minus 5 halves. And the second equation is 5x plus y minus 4z equals minus 1. If I add, these cancel. Minus 5 halves plus 1 is minus 13 halves. Minus 5 halves minus 4 is also minus 13 halves. And minus 5 halves minus 1 is minus 7 halves. So I'm not changing the first equation. But when I add minus 5 times this equation to this, I eliminate the x's and I get this. And then I go to the next equation and I look for the first variable with a non-zero coefficient, and that's the y. So I want to multiply this by something, so the coefficient of y is 1, and I obviously multiply the second equation by minus 2 over 13. So the first equation still doesn't change. If I multiply the second equation by minus 2 over 13, I get y plus z equals 7 over 13. Right. So there's a lot of calculation here, and I'm still not done. But again, if there are any questions as I do this, you just have to stop me and ask. You see, now what I can do, because I have a y here with a coefficient of 1, I can eliminate the y from this equation by subtracting 3 halves times the second equation from the first. All right. Here's my first equation. X plus 3 halves y plus a half z is a half. Let me take this equation and multiply by minus 3 halves. So I get minus 3 halves y minus 3 halves z is minus 3 halves times 7 over 13, which is minus 21 over 26. And then when I add, these cancel, and I get x. A half minus 3 halves is minus z equals, let's see, this is 21 over 26, and a half is the same as 13 over 26. So this looks like it's equal to what is it equal to? Let me make sure I did all my arithmetic correctly. I have x plus 3 halves y plus a half z equals a half, and y plus z equals 7 over 13. So minus 3 halves this, minus 3 halves this. If I add minus 3 halves to 1, I get minus z. Minus 3 halves is minus 21 over 26, 13 over 26. So this is 13 over 26 minus 21 over 26, which is minus 8 over 26, or minus 4 over 13.
Professor.
Yeah.
So after you did the side calculation in the box, so like after that part, because I know like you multiply by -5, like the first equation you
Over
multiply
here.
by, yeah.
Yeah.
I know you multiply by -5 the whole equation, so you could get rid of the x, right?
It's to get rid of the x from the second equation.
Yeah, but like then okay, after that, what do you do after that? Like where you put the two lines inside with the factor, and like what you do with that whole thing?
I'm sorry, there's so much static on your line that it's very hard for me to understand what you're saying. So I have this, I multiply this by -5 and add, and I get an equivalent system of these two equations and two variables, and I've eliminated the x from over here. And then I can make this with coefficient 1 if I multiply the second equation by -2 over 13, and then I get a half and 7 over 13. And then if I add -3 halves times this equation to this equation, let's see, sorry, -3 halves this equation to this, -3 halves, -3 halves, -3 halves times 7 over 13 is -21 over 26. And this is a half, which is 13 over 26. So it looks like I get -8 over 26. And the only reason I'm puzzled is I have something different in my notes, so which is -4 over 13. So it may be that I made a mistake in the notes. So we have x plus 3 halves y plus a half z equals a half, and y plus z looks like it should be -4 over 13. Okay. Oops, I'm sorry. Maybe I'm doing two steps at once. So in this system of equations, when I multiply the second equation by minus 2 over 13, I get 7 over 13. So that is definitely correct. Then I want to take the second equation. I want to take minus 3/2, the second equation, and add it to the first. So if I take the second equation and I multiply it by minus 3/2, I get minus 3/2 y minus 3/2 z is minus 3/2 times 7 over 13, which is minus 21 over 26. And I'm adding this to the first equation, which is x plus 3/2 y plus 1/2 z equal to 1/2. And when I add these cancel and I get x minus z equals 1/2 minus 21 over 26, which is minus 8 over 26 or minus 4 over 13. Yeah, that's good. So I'm not changing the second equation. But if I multiply the second equation by minus 3/2 and add to the first, I get x minus z equals minus 4 over 13. Yes, that's exactly what's in the notes. So everything is good. Now, what does this say? This says that for any z, x is going to be equal to minus 4 over 13 plus z, and y is going to be equal to 7 over thirds minus z. So I started out with the system of equations 2x plus 3y plus z equals 1, and 5x plus y minus 4z equals minus 1. And I did various steps of Gaussian elimination to give me the equations x equals minus 4 over 13 plus z, and y equals 7/3 minus z. And these have the same solutions. So if x, y, z is a solution, x is going to be equal to minus 4 over 13 plus z, and y is going to be 7/3 minus z. I can write that as minus 14 over 3, 7 over 3, and z, right? And 0, plus the vector z minus zz, which is the vector minus 14/3, 7/3, 0, plus z times the vector 1 minus 1, 1. So I've solved the system of equations. The solution space for this system of equations, the solution space, L, let's call it, is the affine space, which is the vector minus 14/3, 7/3, 0, plus all multiples of 1 minus 1, 1.
Wait, how did you get? I'm sorry. How did you get 7 over 3? I have 7 over 13.
I got it by forgetting the 1. It was minus 4 over 13, 7 over, I just forgot the 1 and kept repeating the mistake. Thank you. Yeah. So this vector is a particular solution to the system of homogeneous equations, and this is the general solution to the associated homogeneous system. For the inhomogeneous, this should work. Let's check. So again, our system is 2x plus 3y plus z equals 1, and 5x plus y minus 4z equals minus 1. And what is supposed to be a solution to this system is minus 14 over 3, 7 over 3, 0. So suppose we let x, y, z be the vector minus 4 over 13, 7 over 13, and 0. Let's check. In this first equation, we get 2 times minus 4 over 13 plus 3 times 7 over 13 plus 0. What does that equal to? Minus 8 over 13 plus 21 over 13. 21 minus 8 is 13 over 13 is 1. So that checks. What about in the second equation? 5 times minus 4 over 13 plus y, which is 7 over 13, minus 4 times 0. This is minus 20 over 13 plus 7 over 13 is minus 13 over 13 is minus 1, which also checks. So this is a particular solution to this inhomogeneous system. And what is the associated homogeneous system? It's 2x plus 3y plus z equals 0, and 5x plus y minus 4z equals 0. And what's supposed to be a solution of that is the vector 1 minus 1, 1. So suppose you let x, y, z be 1 minus 1, 1. In this first equation, you get 2 times 1 plus 3 times minus 1 plus 1. That's 2 minus 3 plus 1. That's 0. That checks. In the second equation, it's 5 times 1 plus minus 1 minus 4 times 1. That's 5 minus 1 minus 4. That's 0. It also checks. So this is a solution of the homogeneous system, and this is a particular solution of the inhomogeneous system. So everything that's supposed to work does work, right? It all fits together. Again, this is one of these things where you learn by doing. So the more examples, the more homework problems using Gaussian elimination that you can do, the more familiar you become and the more skillful you become with the technique. That's the whole idea. Okay, any questions? Again, 10 o'clock tomorrow, 4 o'clock tomorrow, I'm available. If not, then we will quit for the day.
Okay, but that's a little confusing. So I'm gonna do some I'm gonna do some of the homework tonight. But is it possible that I can give in the homework fully tomorrow?
You can certainly turn in the homework late. I have no difficulty with that. The only thing I tell everyone is, in summer school, especially, if you start to fall behind, you get very far behind very quickly. But if you turn in the homework late, that's okay. You'll still get full credit for it.
Okay. Because I have the book. I bought the book that was, I guess, recommended. And I'm studying from it. That's why. So I'm kind of
Yeah, but you won't find this material in that book.
No?
No.
Okay.
I don't think so. That what I'm starting with is at a sort of a more basic level than that book starts with. So when we get, next week, what I'm doing next week, I think, is pretty much at the beginning of what's in that book. At least the book the paperback that I recommended, called, I think, Lectures on Linear Algebra. Yeah. It's a really good book to read, but it starts beyond where we are.
Oh, okay.
Right.
Okay, that makes sense.
Because that was a Russian book translated into English, and Russia was way ahead of the United States in math education.
Okay, that makes sense. Okay. And this will be up on YouTube, right? Tonight?
Yep, absolutely.
Okay. Thank you.
So this is section 1.1, exercise 7. So we have the vector 1, 2 times x and the vector 1, 3 times y equals the 0 vector, right?
Mhm.
And we want to say that it has to be the case that x and y are 0. So x times 1, 2, that's the vector x times 2x. And y times 1, 3 is the vector y times 3y, because this is just scalar multiplication. And then when you add the two vectors, you get x plus y and 2x plus 3y. So if this is true, then this vector is exactly equal to this.
Mhm.
And two vectors are equal if they have the same coordinates. So this implies that x plus y has to equal 0 and 2x plus 3y equals 0. But if x
Oh.
plus y is 0, y has to be minus x. And so 2x plus 3y is 2x plus 3. What is y minus x? 2x minus 3x minus x is 0. So that means x is 0, and y, which is minus x, is minus 0, which is 0.
How did you went from y to negative x? What happened to 2x3 plus y? It's the
Well,
first you solved for y
so this
equaling.
vector statement is equivalent to these two equations. X
Okay.
plus y equals 0 and 2x plus 3y equals 0. So
Okay.
if x plus y equals 0, y is equal to minus x.
That is true.
And then I look at the second equation. If y is minus x, 2x plus 3y is 2x plus 3 times minus x.
Oh.
That's 2x minus 3x, which is minus x, but that's equal to 0. So x is 0, and if x is 0, y is 0.
Oh. Okay, negative x. And then negative x equals 0. And then that means that they. Oh, okay. Okay. Can you flip it to so I can see? It says can you move the paper? It's like there you go. Thank you. Okay, so you plugged in the negative x from the y because we solved for y,
Yep.
and then that is equal to negative x, which is equal to 0.
Yep.
Okay.
That's it.
Okie dokie. Thank you so much, Professor.
It's always easy after someone shows you how to do it, but but you sort of study the solution, and then it becomes easy for you too.
Yeah. I just was confused on what to do because it's the whole vector form. I've never seen vector forms before. Like I did vector calculus, yes, but I've never seen vector calculus. That's
Well, this isn't vector calculus.
I mean
This
vector form. Sorry, vector
is
form.
just vectors.
Yeah, it's like I've been like I've been numb at that. It's like dang, but
Well, but
it comes with
algebra
practice.
is about vectors.
Yeah.
And not just in 2 or 3 dimensions, but any number of dimensions. But the dimension doesn't make anything harder or easier. It's irrelevant.
Oh, okay. So that's how it's done. Once again, thank you, Professor.
Okay. All right. We will quit for the day.